Really easy to use MATLAB to get a better understanding and to build your intuition about linear combinations. So in this quick example, we're going to use MATLAB to compute linear combinations of 4 different audio signals so that we can both visualize the signals as plots, but also listen to them to hear what a linear combination really sounds like and to convince yourself that it really is just a mixture of the various signals. So in this case, all of our signals are going to be at CD quality sampling rate. We set up our sampling rate over here, the signals are 145,000 points long, so a couple seconds long, there are going to be 4 different signals. And let's look at the signals. First, there will be a speech signal that is a sample from Shakespeare's play Hamlet. Let's listen to that signal, and let's also plot it.
Alas, poor Yorick.
So this is signal number 1. Signal number 2 is just a sine wave. Let's have a listen to that. So there's signal number 2. Signal number 3 is a chirp, which is like a sine wave, but it has a squared, it's a cosine, but instead of cosine n, it's cosine n squared, and it has a frequency that rises over time. So let's look at that signal and listen to it. Chirps are used in many, many different applications, including radar, sonar, geophysics, understanding the frequency responses of rooms, calibrating speaker systems. Very, very interesting. And you can clearly see here the rising frequency of the signal over time. The final signal, the 4th, is just a good old white Gaussian noise. This is pretty much the same noise that you would hear when you tune in between stations on the FM dial. So now what we're going to do is we're going to take these 4 signals and we're going to create a signal matrix, right? Recall from the previous material that we're going to form a signal matrix X, which is going to be the signal 0, signal 1, signal 2, and signal 3, basically as column vectors. So it's going to be a very tall matrix. It's going to be 145,000 entries tall and very skinny. It's only going to be 4 entries wide. So let's look at how we build up this matrix. It's very, very simple. First, let's just check before we form the matrix that all these signals are in fact the same size and that they're all column vectors, which is very important. So all of the signals in this course, we're going to assume they are column vectors and not row vectors. And we see this is the case, that each of them has 145,000 rows and only 1 single column. So that means we can build a matrix just by concatenating the columns with the comma operator here. And now we've built our X matrix and checked that it has size 145,000 rows and 4 columns. So now we're going to compute linear combinations Y as this big matrix X times a weighting vector A. And this weighting vector A is going to have 4 entries in it, corresponding to the weightings on the speech signal, the sine wave, the chirp, and the noise. And so we're going to just now experiment with some different A vectors, and we're going to listen and plot the results. So the first A vector is all zeros except a 1 in the first entry. What this should do when we form Y equals X times A is it should zero out the sine wave, the chirp, and the noise, and we should hear only Hamlet, and we should also see only Hamlet in the plot. So let's have a listen and have a look.
Alas, poor Yorick.
You can see that all we heard was the first signal, the Hamlet signal, and indeed this is exactly the same signal that we see down here in the linear combination signal y. So that's one possible selection of the A vector. Here's another selection where clearly we should just hear the sine wave, the second component. So let's have a listen and a look to this signal. And we see again that exactly as expected, since A, the only entry in A that's non-zero is the second entry, we basically have all of the sine wave just transmitted through the matrix vector product into the mix. Okay, well let's look at a more interesting mix now. In this case, you can see that the A vector is going to add 1/4 times Hamlet, 0.1 times the sine wave, 0.3 times the chirp, and 0.15 times the noise. It's going to scale the amplitudes of all of these signals according to these entries, and then we're going to sum them using y equals x times A. Let's have a listen and have a look.
Alas, poor Yorick.
So we'll play this a couple times, and you can see that you can hear all of the various components in there, and the weights of each component, or the loudness of it, corresponds to this vector. So let's listen one more time. Oops.
Alas, poor Yorick.
So that is living proof that a linear combination forms a weighted sum of the columns in a signal matrix. Let's say that we're not happy with this mix. Here's a more radio-friendly mix of this signal. You see we've increased the speech, decreased both the chirp and the sine wave, and decreased the noise. So we should hear more of the speaker.
Alas, poor Yorick.
So hopefully this brings home the point that MATLAB is a really useful tool to help us both visualize and hear different signal processing operations, in this case a linear combination. And I invite you to try forming linear combinations on your own and building your intuition into how they work, because they play a really important role in the rest of the class.